Before beginning our discussion of discrete probability distributions, we need to define a couple of terms. First, we need to understand the concept of a random variable. A random variable is really just a numerical description of an experiment, which simply means that when you execute an experiment, it generates a series of outcomes, and the random variable assigns a numeric value to each of the outcomes from the experiment. A discrete random variable has a finite sequence or an infinite sequence of values. These are integer values, they're non-overlapping. And a continuous random variable assigns numerical values in an interval or across a collection of intervals. In order to define a discrete probability distribution, you need to have a list of the outcomes of the random variable, and you need to assign a probability to each of those outcomes. That probability distribution can be displayed as a table or as a graph or even using a formula. So for example, let's take the idea of flipping a coin. If we think of flipping a coin, there are two possible outcomes, heads and tails. We can define a random variable x that assigns a numeric value to each of those outcomes. So we might define x as being 0 if the coin lands on heads, 1 if the coin lands on tails. So now we have a random variable x, and we can assign a probability to each of those outcomes. So the probability that x is equal to 0, or that the coin lands on a head, is 50%, and the probability that x is equal to 1, or that the coin lands on a tail, is also 50%. So the table in the center of this slide essentially defines the probability distribution for flipping a coin. You have the outcomes, you have the random variable, and you have a probability assigned to each one of those outcomes. However, you need to understand that the probabilities have to be true probabilities in the sense that those probabilities do have to be between 0 and 1, and if you add up all of the probabilities across all of the outcomes, those probabilities have to sum to 1, which is of course the case that we have here. 0.5 plus 0.5 would be equal to 1. So that's a probability distribution. It defines probabilities to the outcomes of a random experiment and is subject to the constraints that those probabilities are in fact between 0 and 1, and when you add up the probabilities for all of the outcomes, those probabilities have to sum to 1. A random variable has the concept of an expected value and a variance. The expected value is essentially the mean of the random variable, or the value that we would expect in the long run. So if we were to execute this experiment over and over and over and over again, in the long run, approximately what value would we expect to see as the outcome? So the expected value of x uses the Greek letter mu as a representation, and essentially it is a sum of the values of x, so the outcomes of the random variable, times the probability that that outcome occurs. It's a weighted average where the weights are defined by the probabilities of the outcomes. The expected value doesn't necessarily end up being a value of the random variable. If you think about the expected value of the random variable x that defines the probability distribution, that expected value is not going to be a 0 or a 1, but it's in the long run, where do we average out? Similarly, to compute the variance is just the sum of the squared differences between the random variable, the value of the random variable, and its mean. So we take each outcome, each value, subtract the mean, we square those differences. We multiply them by the likelihood of the outcome, by the probability of the outcome, and then we sum that up. So again, it's a weighted sum of squares, and the weights are defined by the probabilities. Just as in the scenario that we looked at with the sample variance and the sample standard deviation, the standard deviation for a random variable is just the positive square root of the variance. So we have these concepts of expected value and variance, and they can be useful in helping us understand the behavior of a particular random variable or a particular experiment that we're interested in. So let's look at an example. Let's assume that you are involved with operations for Prescott National Bank, and you have to make a decision about how many tellers to schedule at a given point in time during the day. You want to ensure that you have enough tellers to service the customers that are in the bank so that you don't have long queues forming waiting for service, but you also don't want to have tellers who are sitting idly by with nothing to do. And so historically, you've observed the behavior of the customers, you've observed the traffic through the bank, And you might want to try to determine a probability distribution for the number of tellers that are busy with customers at a particular time of the day, say 1 o'clock. It varies from day to day. Certain days of the week the tellers will be busier at 1 o'clock in the afternoon. Other days they will be less busy, just based on different times of the day, times of the week, times of the month, times of the year. And so based on past records, you know what that looks like. You know that at 1 o'clock there's a certain likelihood that 0, 1, 2, 3, 4, 5, or 6 of these tellers will be busy, and you have that distribution available. We'll take a look at that in just a minute. So you might want to ask some questions. If you're trying to determine what your staffing should look like, you want to know what's the probability that exactly 2 of these tellers are busy at 1 o'clock. Or at least 3 of the tellers are busy. If you know that there's a high chance that at least 3 of the tellers are busy, then you want to make sure that you have at least 3 tellers available. On the other hand, if it's not very likely of having 3 or more tellers busy, then you may want to allow some of those tellers to take their lunch break at 1 o'clock. You might want to know what's the probability that fewer than 2 tellers are busy at 1 p.m. And you may also want to ask a question like, exactly how many tellers would I expect to be busy over the long run with customers at 1 o'clock? So here's our distribution. This is a probability distribution. There are 6 tellers, and so you could either have 0, 1, 2, 3, 4, 5, or 6 of those tellers busy with customers, and you can see the probabilities on the right-hand side of that distribution. If you add those probabilities up, they do add up to 1. So the likelihood of no one being busy at 1 o'clock in the afternoon is only about 2.9%. The probabilities peak at 5 tellers busy with customers. There's a little over 26% chance that 5 of those tellers will be busy with customers. If we wanted to compute probabilities based on this distribution, these are discrete values. So it's not possible that exactly 1 and exactly 2 customers are busy at the same time. So these are discrete values. They're mutually exclusive. And so we can think about the law of addition with mutual exclusivity. We can compute the probabilities by just simply adding up the values of the probability for the outcomes of interest. And so our first question asked, what's the probability that exactly 2 of these tellers are busy at 1 o'clock in the afternoon? So we say the probability that x is equal to 2, and we can just read that off of our graph. So the probability that x is equal to 2 is just 0.078. Our second question asks, what's the probability that at least 3 of the tellers are busy? So at least 3 would be 3, 4, 5, or 6. So we're interested in these outcomes. And so in order to compute the probability that x is greater than or equal to 3, that it's at least 3, we would add up the probabilities over here on the right. So 0.155 plus 0.212 plus 0.262 plus 0.215, and if we do that, it turns out that that probability is 0.844. And last but not least, we wanted to know the probability that less than 2, fewer than 2 tellers are busy. So fewer than 2 would either be 0 or 1. So again, if we wanted to know the probability that x is less than 2, right, we could add up those probabilities, 0.029 plus 0.049, and that would give us 0.078. So now we can begin to get a feel for what the staffing is going to look like. We know that there's a pretty slim chance of exactly 2 tellers being busy, but we can see that the probability of at least 3 tellers being busy is about 84%. So there's a pretty high probability that you're going to have 3 or more tellers busy. You probably want to make sure that you keep a good number of those tellers around during the 1 o'clock hour, because there's a good chance that those tellers are going to be busy. So at least 3 tellers are likely to be busy in the 1 o'clock time frame. The last question asks how many tellers we would expect to be busy at 1 o'clock, and so that's a slightly different question. That's not really asking about a probability, it's asking more of a number. And in order to answer that question, we could compute the expected value. So again, the expected value of a random variable is equal to the weighted sum of the observations. So we would take the value, the outcome of the random variable at 0. We would multiply 0 times the probability that x is equal to 0. And you can see in that right-hand column that value would be 0. We can take 1 times the probability x is equal to 1, that gives us 0.049. 2 times the probability that x is equal to 0.078, that gives us 0.156, and so forth. And then we just add up those weighted values. So if we add 0.000 plus 0.049 plus 0.156, if we add all of those values up, the expected number of tellers that would be busy at 1 o'clock in the afternoon is 4.118. Since you can't have a fractional teller, then we would say approximately 4 tellers are likely to be busy with customers at 1 o'clock in the afternoon. So that's how we can begin to use probability distributions, and in particular discrete probability distributions, to help us understand behavior in a business context. The Prescott Bank example is a very specific example of a discrete probability distribution, but there are a number of more general probability distributions that have been studied and that are very well defined, and we're going to look at one such discrete probability distribution in the next lecture.